Welcome to my series on graph theory. This first lesson is an introduction. I'll just go over a simple problem and then some terminology. And then in subsequent lessons, I'll get into more details. Graph theory began not as abstract mathematics, but as a fun puzzle about walking through a city. In the 18th century, the city of Königsberg, now Kaliningrad, Russia, had 7 bridges connecting 4 land masses across the Pregel River. I'll show you a diagram of this on the next slide. Locals wondered, is it possible to walk through the city, crossing each bridge exactly once and return to the starting point? In 1736, the famous mathematician Leonhard Euler proved that this was impossible. Euler modeled the problem by treating the land masses as dots or vertices and the bridges as lines. This abstraction is now considered the birth of graph theory. Okay, so let's have a look at the problem, and then we'll talk a little bit about some terminology in general for graphs. Here's the diagram for the situation. So we have this river that comes into a town, Königsberg, and it splits here, then it reunites, and then it splits again. And so it kind of separates the city into these 4 regions. The region above the river, A, the region enclosed here, B, this region, D here, and then the region below the river, C. And the task, which is impossible, but the task that's being asked is, can you start at A, for example, and go over each one of these bridges once, and then come back to A. So you need to go over each bridge exactly once, I should say, and then return back to your starting point. So that's not possible, and I'll show you why in the next slide. I copied the diagram from the previous slide up here at the top, and the first thing I want to do is show the insight from Euler in taking this physical picture and casting it as a graph. So each one of these regions is what's called a vertex, and then the connectivity between the regions are shown with these edges here. So for example, you have A goes to B either through this bridge or through this bridge. So we represent it by these 2 edges here. C can go to B from 2 different bridges. So we have that here. B to D is this edge here, A to D, and C to D are this and this here. So that's the first insight. The other insight's a little bit harder to see. Each one of these vertices has an odd number of edges on it. You notice here it's 3, 5, 3, and 3. And in general, if you want to have a loop, a circuit where you start from a vertex and come back to it, you have to have all even vertices, all vertices that have an even number of edges coming in and out of them. And in case here we have just the opposite; they're all odd. And the problem is, I'll just illustrate it maybe with one of these here. Let's say we start with A, and we want to come back to A. So C is an intermediate point, but we need to cover this edge, and this edge, which are 3 different bridges, right? So we have to enter C, and then we leave it, and in order to cover this edge here, we would have to come back along in this direction here from D to C somehow, but then you'd be stuck, right, because you've already used up your one crossing of these 2 bridges here. And then it's the same problem with B and D. So it doesn't work because we have all odd vertices. And I'll show you how to solve this by adding more bridges on the next slide. So on the left, we have a partial solution. I've added another bridge here from C to D. And by the way, all these edges are bidirectional. It's just because of the problem we're modeling. The bridges, of course, you can go over them in either direction. So by adding this, let's just check the number of edges on each one of these vertices. So this is still 3, so this is odd. This is 5, so this is odd. But then this is 1, 2, 3, 4. So this is even, and this is even. So if you have two odd vertices, you still can have a loop, but you can have a traverse where you go over each bridge once, and the only problem is that you end up in a area different from where you started. And I have these numbered here just to show you what I mean. So you can go from, let's say we start at A. So we're not going to be able to get back to A and cross each bridge exactly once, but we can get back to B and then fit and cross each bridge once. So you go from A to B, B to C, then C to D. So that's the third. Then D to C, C to B, B to D, D to A, and then A to B. Okay, so that's a path from A to B where you cross each bridge exactly once. That wasn't possible in the previous version that we looked at. So we still don't have what we want. The problem said, how do we get back to A? And we've established that's impossible. But out of curiosity, we want to see, well, how do we fix this so that we could have a series, a circuit that we start at A and get back to A. So I've added yet another edge here, another bridge, and that'll allow us to get back to A. So we go through the same path we had here, and this additional bridge lets us get back from B to A. And if you notice now, this A has 4 edges on it. B has 1, 2, 3, 4, 5, 6. So this is even. This is 4 again, so this is even, and this is 4. And that's the general solution to the problem. So we could have a much more complex graph with a lot of vertices and edges. And if we check that all of the vertices are even, then we'll know that you can form a circuit that goes from any one of the vertices and returns to it while crossing each one of the edges exactly once. That's a general theorem. We'll get to that later. I just wanted to kind of inspire you in terms of the type of problems that could be solved with graph theory. And this is the very, very first example. There's many other examples, but this is the first application. So we saw our first example. I just want to put down some definitions here. Some of the terms we've seen already. Graph theory studies mathematical structures used to model pairwise relationships between objects. The graph G is an ordered pair of two sets, really, a set of vertices and a set of edges. The vertices are sometimes called nodes or points, and the edges are sometimes called links or arcs. The vertices represent entities, person, city, an area within a city, as in our example that we just saw, computers, web pages, molecules. And then the edges represent a relationship or a connectivity between vertices. So in our example, we had bridges that represented the connectivity, and we used an edge in our graph to represent the bridges. Then we have undirected graphs where edges have no direction and all the relationships are symmetric. So this is most common for introductory examples. Then we have directed graphs or digraphs where the edges, each edge has a direction, so the relationships are asymmetric. And that can be used to model things like one-way streets, follower or following, web links, and other types of dependencies. I have a few more definitions here. Two vertices are said to be adjacent if they're connected by an edge. So for example, A and D are adjacent, B and C are adjacent. However, A and, for example, C are not adjacent because you need to go through two edges to get between them. We already saw the concept of a degree. That's the number of edges connected to it. So A, for example, would have degree 4. B has degree 1, 2, 3, 4, 6. We counted that before. And we haven't looked at a directed graph yet, but you have to count the in in the out degree in that case. We'll get to that later. A path is a sequence of vertices connected by edges. So for example, if we went from A on this edge here to B, let's say from B to C on this edge here, and then from C to D on this edge here, that would be a path. A cycle is a path that starts and ends at the same vertex with no repeated vertices. So what our problem that we solved, the Königsberg problem, which we solved by adding bridges, that's not a cycle because we crossed some of the vertices more than once. It's the edges that we only went over once. That's something different from a cycle. A cycle would be A to B and then B to A. So there you don't cross the same vertex more than once. So that would be an example of a cycle. Another cycle would be A to B to D to A. That would be a cycle. And let's give you an example of something that's not a cycle. If you went from A to B and B to C, and then you use these different edges to get back, C to B, B to A, that would not be a cycle because you crossed B twice. Then we have a connected graph. This would be an example of a connected graph. And if we had another graph up here, for example, and it had no edges to A, B, C, or D, then that would be a disconnected graph. Basically multiple graphs that have no connectivity between them. Okay, so that's the last slide in this lesson. If you like this, please give it a thumbs up. I have several more lessons coming that'll get into more details in terms of theorems and their proofs and some more examples.